Good evening.
It's empty? Oh, no, it's full.
So as you are all so silent and in expectation, I will start, I guess. So good evening, dear colleagues, dear friends, dear members of the ProISSI Association. It's my very great pleasure to welcome you to our tonight's evening talk, and it's my even greater pleasure to introduce to you our tonight's speaker. So it's Professor Gary Zank, who will give us a talk on faltering steps into the galaxy, and I would like to very briefly recapitulate a little bit the key points of the career of our speaker that we are very pleased to have with us tonight. So Gary Zank studied applied mathematics and physics at the University of Natal in Durban in South Africa, where he graduated in 1983 and concluded his PhD studies in 1987 in applied mathematics. He then moved on to Europe, to Germany to be more specific, as a postdoctoral fellow to the Max Planck Institute for Kernphysik in Heidelberg, where he stayed for 2 years between 87 and 89, then followed by a short additional postdoctoral fellowship at the Max Planck Institute for Aeronomy in Lindau, also Germany. He moved to the Bartol Research Institute of the University of Delaware as a postdoctoral research associate in 1989. There he stayed for several years. In 1991, he became assistant professor. In 1994, associate professor. And eventually in 1999, he became full professor. In 2001, he moved on, so that's typical for scientists. They are always on the move, so it's also in his case like this. He became director of the University of California in Riverside, director of the Institute of Geophysics and Planetary Physics, 2001, until quite a long time. He stayed there until 2008, when he moved again to the University of Alabama, Huntsville, where it's also his current affiliation still today, where he is the director of the Center for Space Physics and Aeronomy Research. And in 2010, he also became the chair of the physics department. This is the professional career of our tonight's speaker. So concerning research, he is a specialist in space and solar physics, plasma physics, and computational physics. And he has a long list of awards and fellowships, where I would just like to cite a couple of ones that are very prestigious, I think. The Seldovich Medal he received from the COSPAR, Committee of Space Research, for his work on space plasma physics, and in particular for his theoretical studies of mass loading shock formation in interplanetary space and of the interaction of the heliosphere with the local interstellar medium. He became fellow of the American Physical Society for fundamental contributions to the understanding of shocks, particle accelerations and plasma turbulence, and to studies of the solar wind corona, interplanetary shocks, and global heliosphere structure. And in 2015, the Oxford Medal, which is the highest honor awarded by the Asia Oceanic Geoscience Society, for his seminal contribution to our understanding of the evolution and properties of the solar wind, magnetohydrodynamics turbulence, structures in the outer heliosphere, and particle acceleration and transparent throughout the heliosphere, and for his exceptional leadership in the general space plasma community and development of space physics within Asia and Oceania. As we are here in Bern, of course, I have to mention the Johannes Geiss Fellowship. That's the main reason maybe that you are here tonight. Thanks again for coming. So he was elected the ISSI Johannes Geiss Fellowship in 2017. As you can imagine, the publication record and stuff like this is very long, so I will not read it. I will just try to highlight that with more than 550 publications, 21 edited books and 2 textbooks, and the third one I read is now in progress, he is definitely a leader in his field, and I'm very much pleased that he's here tonight to introduce to us to this fascinating topic about these faltering steps into the galaxy. So please, Gary Zank, the floor is yours.
Well, thank you very much for that very nice introduction. While I was sitting there, I guess I wasn't listening terribly much to it, since I kind of know it. And I was kind of struck by what an odd language English is, since I noticed it says Board of Trustees, Trustee Professor. And I don't know how many of you are aware that there's a curious English sentence which uses one word only, and it's one word that might not typically come to many of you, and so if you're not quite sure about it, I can explain it afterwards. But the sentence is buffalo, 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 and it's a genuine sentence in English. Anyway, you can ponder on that while you think a little bit about this. So I noticed there are a lot of old friends in the audience. In fact, some of them go back perhaps 50 years, when I was 6 or 7 years old, and some others who've known me for over 30 years, and others in the audience who have known me for not quite as long, but for a very long time. And so I'm particularly gratified to see all of you here. It's a real honor for me. And if my mom and dad have managed to figure out their computer, they may even be watching as well via the live stream. So I should at least say hello to them. In any event, when putting together this presentation, I realized that, in fact, the very first conference of ISSI was, in fact, on the theme that I'm going to talk about today. I remember in 1996 attending that meeting, and I think the volume 1 is downstairs on the bookshelf, and it was the physics of the interstellar medium. And back in 1996, it was a very exciting, very rapidly developing field. And so there was lots of theoretical modeling being done. There were lots of anticipated results to come, but I thought this would actually be a very nice way to close that. I was at the very first of those conferences, symposia, workshops, and this is kind of an update from 1996. So let's see if we don't make this work. So I thought I'd first start. I think many of you probably know Ed Stone, and this was a NASA press press conference that was held. I was fortunate enough to be part of it.
You are about to hear a discussion of a first in the history of exploration. The most distant human-made object, NASA's Voyager 1 spacecraft, is in interstellar space, the space between the stars.
So this was this press conference was held in 2013, and what he was talking about was an event that had occurred the year before, and to sort of place that into a little significance.
Today is the current moment for NASA, the Voyager team, and in fact, humankind.
And so, I think, looking around the room, that many of you were at the dawn of the space age. I remember in South Africa, I was quite fortunate to, we didn't have TV in South Africa at the time, and in 1969, with the moon landing, we were all bused from our school to the local Fox cinema theater, where we watched Neil Armstrong set foot on the moon for the first time. And I remember what an astonishing, just extraordinary event that happened to be. I was always interested in stars, planets, and things, even as a very small boy. And so in some sense, this kind of propelled my enthusiasm and interest even more. And so in 1977, this was still while I was at high school, that sort of space age culminated in the launching of two spacecraft, the Voyager 1 and the Voyager 2. This was in 1977. I think the one was in September and the other was possibly a couple of months earlier. I think Voyager 2 launched first and then Voyager 1. That's the launch, and that's just an image of Voyager, of the Voyager spacecraft. They're both identical. I learned later, when I was giving a presentation there, I had somebody in Huntsville come up to me and tell me that they had, in fact, well, he owned the company that had built some of the electronics for the Voyager spacecraft. And Huntsville, I think I have it in the next presentation. Yeah. Huntsville, in case many of you are unaware, in fact, in some respects, is the birthplace of space exploration, certainly in the US. Wernher von Braun was originally brought to Huntsville to develop the US missile program as a result of his work during the Second World War. And Redstone Arsenal was the location where all of this took place. And so, of course, with the launch of Sputnik, the US promptly tried to get into the civilian space investigations as well. And so von Braun was kind of working across the Army and the then civilian space program. But Huntsville was, in fact, the place where all of those missiles were conceived, developed, and built, and culminated in the construction of the Saturn V rocket, which, and this is a photograph, that's a model replica of the Saturn V. You can see it as you drive past, as you drive down the highway 565 in Huntsville. You can see it as you fly into Huntsville or fly out of Huntsville. It's the most memorable beacon, if you like, of the city. I think that's a Saturn I on the left. Has this fantastic museum, which also includes a real live Saturn V rocket, this time on its side, kind of split up. And so when dignitaries and other people visit, or there are conferences, typically a dinner will be held underneath the Saturn V rocket in Huntsville. So Huntsville played an integral role in space exploration and even contributed to Voyager, which is the story I'm going to tell you a little bit about tonight. So that is the Voyager spacecraft. And it has a suite of instruments. This is one that's particularly important. Well, this is the boom on which a magnetometer, an instrument to measure the magnetic fields in the interplanetary and now interstellar medium. And we'll talk a little bit about the observations that come from that. There's several cosmic ray instruments and a low energy. By low energy, these are still many keV, up to about an MeV of energy for the low energy charged particle instrument over there. Also a very important player in much of the story. This is the cosmic rays, which measure both anomalous and galactic cosmic rays, and I'll talk a little bit about that. There's another instrument over here, which is the sort of plasma wave antenna, and that's going to also play a central role in our story. It's interesting that this whole thing is just powered by 3 RTGs. So these RTGs over here, radio isotope thermoelectric generators, basically have a little lump of plutonium, very small lump of plutonium, that heats one of these thermocouples and provides the electricity that powers all this instrumentation and keeps the spacecraft warm. Unfortunately, plutonium, as you know, has a half-life, which is rather short, and so by about 2025 or so, it's now anticipated that the power for the spacecraft will no longer be sufficient to, in fact, power the instruments and keep the spacecraft warm. And so this whole thing will eventually go to sleep, shut down, and no longer be sending signals back to us. Just a reminder as well about the computational advanced state of the Voyager spacecraft. if some of you remember, there was a mission called the Viking mission that went to Mars, and so the computer command subsystem is based on that early 1970s technology. So all of your smartphones and even some of your not so smart smartphones have far more computational capabilities than is used to run the spacecraft. So this is 1970s technology, and it also has, I should say, a gold record on it. The gold record is supposed to be a sort of statement, story, testimony of humankind, and so it was developed by Carl Sagan and a team of people that were interested in trying to where we lived, what it was we did, spoke, ate, and so forth. And this is a replica of the gold of that gold disc that's attached to both spacecraft. This was actually at the Voyager press conference that I mentioned before. So we're in 1970s technology, and we've got a spacecraft that has now exited the, I'll talk to you a little bit more about that, but in principle has exited, if you like, the heliosphere, the solar system. And so the fate of the spacecraft once it goes to sleep is to simply head off towards the stars. I'll mention which stars in a few minutes, but really, its fate is to spend the next several billion years simply orbiting the galactic center, going round and round and round. And if we ever, and in some sense, this is our legacy to the universe, to the galaxy, which I find exceedingly depressing. I know some of you probably went through the 1970s, but honestly, the clothes, the culture, the sort of shag green rugs, the sofas. Really, I don't think this was a high point of our civilization at all. This, in fact, is a photograph of Elvis's room. I think it's just called the Jungle Room. If you look over there, for example, you'll notice this attractive chair with some form of covering, heaven only knows what, and what look like eagles. There's a waterfall that runs down there, but the shag green carpet. Anyway, this is what people who were wealthy aspired to. So, the other thing I actually asked my audience, but I'm not going to ask this audience because I suspect most of you know what an 8-track cassette is. But generally, many of the audiences to whom I speak, they're much younger. No disrespect to any of you, but they're generally a lot younger than this audience, and most of them have no idea about what an 8-track cassette is. And this is essentially what is used on the Voyager spacecraft to record the data. So it's absolutely remarkable to me that the Voyagers, launched in 1977 and 41 years old, still have a magnetic tape that goes round and round and round and has been doing so continuously for 41 years and collecting data, recording that data, sending that data back. I don't know how many of you bought, for example, a CD player or a cassette player, but I'll wager that not one of you has one that works. But this has been going for 41 years. Also on the one instrument, the LECP, the low energy charged particle instrument on Voyager, it basically has a little stepper motor that just keeps rotating around and collecting particles as it flies through space. And that stepper motor has been going continuously for 41 years as well. I mean, when you think about it, it's just a remarkable feat of engineering that they can do that on a spacecraft, but they can't make our washing machines or our tumble dryers or anything else actually last for much longer than about 3 or 4 years. Anyway, that's probably enough about the 1970s. So I thought I'd start out and go inwards. And so what I wanted to do is just to look whereabouts are we and is Voyager. And so this is a sort of view, if you look right down from the North Galactic Pole, looking down onto the galaxy. And it's kind of zoomed in, believe it or not, but these scales are enormous. You can see that's 100 parsec scale over there. And this is more or less the geography of where we are. And so what we've been in, and possibly still are on the outskirts of, is a very hot interstellar medium region with temperatures on the order of about 1,000,000 degrees Kelvin. It was probably created by one or more supernova remnants that had gone off and created this great big kind of bubble or void in the in the galactic or interstellar medium. This is the sun, obviously not to scale, and this gives you a sense of how it's moving relative to this overall structure. And you can see there these kind of wispy things that are sketched out in the blue there, and those wisps are essentially or possibly material that's been created on the edge of this great big bubble of hot material. And so this stuff that you're going through has typically got a quite complicated cloud-like structure. It has much, much lower temperatures than the hot interstellar medium, and so those temperatures are probably on the order of 10,000 degrees Kelvin. When you're at a temperature of about 10,000 degrees Kelvin, the plasma, the material in which you find yourself, is no longer fully ionized typically. So this material is typically partially ionized. It's a mixture of protons, electrons, other heavy ions, but also a lot of neutral gas, hydrogen atoms, helium atoms, and some other neon and so forth species. Most of it is neutral hydrogen, though, and typically not. It's typically in its atomic rather than a molecular state. The other thing is the sun sort of also orbits the center of the galaxy, and it has a period of about 33 million years. And as it orbits, it goes up and down inside the galactic plane with an amplitude of about 80 parsecs. So if you look even more closely at our galactic neighborhood, this has become a region of great interest to a lot of people now. Again, here's the sun. This is its sort of general sort of sense of motion relative to the galaxy. And this is one of those wisps that I was pointing out. This is more or less called, very imaginatively, the local cloud, or the local interstellar cloud. Right next door to our current nearest neighbor is another cloud, the G cloud, that surrounds Alpha Centauri, has properties slightly different from the local cloud. And as a result of some of this work, what you see here are various forms of bow shocks or structures, a little bit like a boat plowing through the water and creating a bow wave. If it moves supersonically, it produces a bow shock. And so you can see that a number of these have been identified as bow shocks. How they're identified and why they're identified as such, I may or may not touch on in a little later. Also, interestingly enough, a lot of those stars have been identified as having planets. So this is also very interesting in terms of exoplanets. So here's the picture that was on the card. And this is a picture that tries to give you now a sense of scale. So we've come in yet further. And so again, there's the sun. And there's Alpha Centauri that I'd pointed out a little bit earlier, and I'm not sure how easily visible this scale is. Obviously, these are the planets all lying in the ecliptic plane, and you've got all the Kuiper Belt objects outside here. You've got the Oort cloud, which technically means that the solar system probably extends out to there if you include the Oort cloud as part of the solar system. The heliosphere is basically bounded by this region over here, this sort of funny pink color over sort of over there. So what you have is you have the wind, the solar wind, the supersonic wind that comes from the sun. As it expands radially, it pushes into the interstellar medium and creates a great big bubble. That bubble is called the heliosphere. And there's a boundary between the solar material and the interstellar material. That boundary of the heliosphere is called the heliopause. I'll point those out again in a few minutes. So the heliopause separates in principle solar material from interstellar material. So if you cross the heliopause, you go from the solar material side to the interstellar material side. Everything inside here, not quite everything, as Peter Bochsler will point out, I'm sure, but almost everything. Actually, that's not even correct. Most of what we think of inside here is material from the sun. But I'll point out that there's some very interesting material that gets through from the interstellar medium. So this wind expands supersonically, and as it expands, it creates this great big bubble. But eventually you have to decelerate that flow, and that flow is decelerated at something called a termination shock. And so this is the heliospheric termination shock, where you take the supersonic flowing solar wind, decelerate it to a subsonic state, and then that inner region is called the inner heliosheath. And then if you are, in fact, moving fast enough with respect to the interstellar medium, you'll also produce something that looks like a bow shock. And there's a lot of debate currently about whether it really is a bow shock or whether it's a bow wave. And that depends on the properties of the interstellar medium. And the properties of the interstellar medium can, in fact, be mediated by the behavior of the interstellar medium in a complicated way. Okay. So these are those boundaries again, I pointed out. So this is maybe an easier three-dimensional view. Oh, I should maybe go back. So these scales over here, this is about from the sun to our nearest neighbor Alpha Cen is about 1.6 light years in distance. This is on a logarithmic scale, so you can kind of squeeze these distances in. So 10 astronomical units, which is roughly where Jupiter is 1.3 light hours. So you can get a sense of just how much larger that scale is. And this distance to the heliopause is on the order of about 124 astronomical units. And I'll use the word astronomical units frequently, but an astronomical unit is the distance from the sun to the Earth. And it's just an easier way of thinking of distance scales. All right, so these are the boundaries as I indicated. So there's my supersonic bubble bounded by the termination shock. Here's my heliopause, which separates solar material from interstellar material, and that's my possible bow shock. You'll notice that the Voyager 1 and the Voyager 2 trajectories are in different directions. The Voyager 1 goes northward, and the Voyager 2 trajectory goes southward. This was after the last of the planetary encounters, where there was a gravitational assist that took one up and one down. So what's nice about that is that we're basically exploring both sides of our heliosphere, both in the northern and in the southern directions. And I think the following gives another sort of version of that, maybe with a little more physics in. Just some quick facts, because people are quite interested in this. Voyager 1 and Voyager 2 are now the furthest human objects from the Earth. And I looked this up a couple of days ago just to get the real number. If you go to the NASA JPL site, you sort of see the numbers scrolling through as you look at it. The spacecraft are moving at a speed of about 3.6 AU per year. So that's 3.6 times the distance from the sun to the Earth. And that's the distance that they move in a year. So Voyager 1, I'm sorry about miles, but Voyager 1 is approximately 13.1 billion miles from the sun, roughly at 141 astronomical units, so 141 times further from the sun than the Earth is. And Voyager 2 is lagging behind at 10.9 billion miles, and it's at roughly 117 astronomical units. Just to put that into sort of perspective, Pluto is just a little less than 4 billion miles from the sun. So this is so roughly 40 AU. So this is much, much further, more than 3 times as far from the sun as Pluto is. This is, I always find, quite staggering. If you send out a signal to tell the spacecraft to turn right or to turn left, it's going to take you 19.5 hours for that signal to get there and for the spacecraft to respond. Oh, and the other thing is, up there and down there, they're separated by more than 9.1 billion miles, so an enormous distance. So Voyager 1 and Voyager 2 eventually crossed that first of those boundaries, which is the termination shock. That's the region where the flow goes from supersonic to subsonic. And so Voyager 1 crossed in right 16th of December, in 2004 at 94 astronomical units. So that meeting that I alluded to in 1996, we were still another 8 years before crossing, and the interest and the speculation about exactly how that crossing would take place was quite intense at the time. And then 3 years later, or a little less than 3 years later, at a roughly 84 astronomical units in the southern hemisphere, Voyager 2 crossed. And I don't have a figure showing it, I have it in another talk, but as you might imagine, for any mission of this kind of length, there were considerable pressures to cancel the mission or to terminate the mission. The idea that, you know, once you'd passed the major planets, because remember, Voyager 1 and 2, the original Voyager mission was to explore the outer planets and certainly not to go out and explore the boundaries of the heliosphere. Although the original mission, or at least the original concept of that mission, was in fact to go a long way out. Voyager was launched to take advantage of the sort of configuration of all the outer planets. They were all just ideally aligned for a spacecraft to go from one to the other of the outer planets and explore each of them. And so the mission was conceived for that. But and I remember talking to Ian Axford, who was one of the people who was very strongly in favor of this mission. All of the scientists really believed this would also be an opportunity to, in fact, explore the distant reaches of the heliosphere, including the boundaries. But of course, nobody back then knew where the boundaries were. And some of those boundaries, the location of the termination shock, for example, was originally one model back in the in the early 70s, in fact, suggested as close as 10 astronomical units. I think that was by Dessler, I think, had some paper along those lines. But then it extended to all sorts of distances greater than that. And of course, once the planetary mission had happened, the spacecraft just kept on going and going and going. And you know, the scientists were fascinated because we were learning about cosmic rays, we were learning about magnetic fields and other energetic particles as we went further and further out. But of course, a politician tends to care very little about cosmic rays, or even less about magnetic fields. And so there was considerable pressure both from Congress and actually within NASA, because of course other scientists were wanting to launch another more exciting mission to somewhere else, and of course they would prefer to have that funding. So I remember at one meeting in Potsdam prior to this crossing that Ed Stone was supposed to give a talk, and in fact was called back very quickly to Washington to try to justify why the Voyagers should continue going. In fact, and I think Peter Boxler may have even been at this meeting, or several meetings that used to be held in New Hampshire about the interaction of the solar wind with the interstellar medium. And the question always arose as to when are the Voyagers likely to cross the termination shock? And so they had a little poll at the end of each of these meetings that would then be distributed to all of us who were there, and you had to sort of pick your favorite distance. And invariably, I guess it became something of a joke, but invariably, the answer that was most popular was 10 astronomical units ahead of the Voyager spacecraft. And it turned out that in fact was the correct answer, at least when we got to within 10 astronomical units of the termination shock, because the termination shock is highly variable and moves in and out in response to changes of the solar wind pressure, the ram pressure. And we have some simulations where we actually managed to predict the crossing of the Voyager 2 spacecraft. This was a paper that Haru Washimi and I and some other Japanese co-authors wrote, where we predicted that we would cross the termination shock. Voyager 2 would cross the termination shock in October of 2007. Well, it turned out to be October. It turned out to be late August. And considering the scale, I think it's a pretty reasonable prediction that worked out. But when you looked at the way in which the crossing occurred, what in fact happened was that the termination shock, because the solar wind ram pressure had changed, the termination shock was moving out for about 5 years, just at the same speed as the spacecraft was approaching, and we would see these odd signals from the termination shock, odd signals associated with what seemed to be reflected particles coming back from a shock somewhere out there, but we never quite reached the shock, and the reason was the shock was moving and moving and moving at the same speed as the Voyager 2 spacecraft was moving, and so this crossing never happened until August. And the crossing itself, in fact, was quite remarkable, because it turns out that once we went through this detailed analysis, it turned out that at that point the shock was coming in. And so the shock was coming in and the Voyager 2 spacecraft was going out, and they were able to intersect. And the reason the shock was coming in was because much, much earlier, several years earlier, in fact, a very large shock wave had propagated through the heliosphere, across the termination shock, propagated through the inner heliosheath, reached the heliopause, which is a much, much more dense structure, reflected, and part of it, and the reflected shock then propagated back towards the termination shock, collided with the termination shock, drove the termination shock inwards, and that was when we crossed the termination shock. So the physics of how all of this happens is really, really remarkable, but Voyager 2 have now crossed the termination shock. So the next important boundary then to discover, and by the way, once the Voyager 1 and 2 spacecraft had crossed the termination shock, we've had no problem with Voyager continuing to get funded. So if nothing else, that discovery turned out to be a lifesaver. So the Voyager 1 spacecraft then was going through this very complicated region downstream of the termination shock, behind the termination shock, measuring magnetic fields, measuring energetic particles. And this was essentially what it was, at least the magnetic instrument, the magnetometer, was seeing. This is the magnetic field, this is the intensity of the magnetic field, and these are the directions of the magnetic field. And what you see in going through this is that the magnetic field will flip direction frequently from one side to the other. And that's associated actually with the behavior of the sun and the way it turns, because the sort of rotational axis and the magnetic axis of the sun are misaligned a little. And so what happens is you produce a region which is called the heliospheric current sheet, where you don't really have magnetic field, but the magnetic field swaps from one side to the other, and this structure has a kind of ballerina form and so what this over here is exhibiting is the heliospheric current sheet being carried into the inner heliosheath on the other side of the other side of the termination shock. So that all looks very nice, but as you get to higher and higher latitudes, you start seeing fewer and fewer of these crossings. And then and so this was interesting, but something interesting started happening sort of late in 2011, early 2012, where the magnetic field intensity started getting larger and larger. And this was during a period for a while where the field was oriented primarily in one direction and then in another direction. Flow was getting smaller and smaller. In fact, it seemed to be zero at some points, and at other times it seemed to be coming inwards. And so something interesting was happening here, and you can see it more in this shorter plot, which is now, this is just 2012, and this is days of the year during the year 2012. And again, there's the magnetic field, and you see these very, lots of variation. This is sort of during this rising period, and you see sort of dropouts, curious dropouts that seem to drop quite suddenly and then get quite high, much, much higher. And these fields are very, very small. It's 0.2, 0.1, 0.3 nanotesla. And you can see that there's this sort of constant unipolar direction, away polarity, and then you get something that jumps there and then comes up. But after this, so if I just look at the magnetic field, after this period, everything just suddenly becomes more or less stable, with a field that's much larger than we've seen before. It's about 0.4 nanotesla, which is, good 2 times larger than we had been seeing. And also, if you looked at the direction, you see that the direction just suddenly settles down into this very, very smooth, kind of unchanging state. and it's oriented like that. Then if you had a look at the particles, these are the energetic particles. What you see is that you saw lots and lots of energetic particles. These are all the energetic particles that you see inside the inner heliosheath. And then there are these dips, which seem to be coincident with these big changes in the magnetic field intensity. And then at about that point where everything went quiet and everything went steady, you suddenly saw that all those particles just seemed to vanish. And you see that there's this kind of exponential almost drop off. There's a scale length that's related possibly to a diffusion length scale over there, and suddenly you see no more particles. And so when this was all put together and we saw this, everybody immediately said, aha, we must have crossed the heliopause. The heliopause, remember I told you, was this bound separated solar material from interstellar material. And these energetic particles at half MeV are typically like anomalous cosmic rays. So they're confined within this inner heliosheath by the heliopause. And so when you left the heliopause, the expectation is you would no longer see these particles. Instead, what you would see is galactic cosmic rays predominantly. And I'll show you a figure where, in fact, you see a sudden step increase in that. So everybody said, aha, we must have crossed the heliopause. We must now be in interstellar space. The complication was, if you look over here, you see that the magnetic field direction going from this side to over here, which you can normally call the inner heliosheath, to this side, something else, that field direction hasn't changed very much. And that's kind of a surprise. You wouldn't, in some sense, and this is, I sometimes think my observational colleagues spend too little time reading the theory and modeling papers that they should be reading. But this was kind of the observational expectation that was there. If you had an interstellar magnetic field, if you had the heliopause over here and you had the magnetic field of the interplanetary medium, remember the magnetic field of the interplanetary medium is a sort of dipolar-like field. The sun is spinning on about 27 days. Every 27 days, and it wraps up the interplanetary magnetic field into a great big tornado-like structure. So that's illustrated over there. So if you took some orientation of an interstellar magnetic field, your expectation, if you didn't think about it or do all the modeling that was related to perhaps the situation, would be that there would be a big change in magnetic field direction and possibly strength as you went from the heliopause, where it's interplanetary magnetic field, the sun's magnetic field, to the interstellar magnetic field. And so when you do this, you don't expect there to be a very, very small change. And in fact, Len Belager and Norm Ness is the principal investigator on the magnetometer. They in fact argue that the direction of the magnetic field scarcely changed, despite the large changes that were seen in the energetic particles. And so they argued that, in fact, Voyager 1 remained in the heliosheath and that it just simply entered a new inner heliosheath region at this time and has remained in that region. There were those series of bumps and wiggles. And so they argued that we had not, in fact, crossed the heliopause. So scientists, Ed Stone and others, well, if you need a new name, there's the helio cliff, because the helio cliff, as that figure showed, where the particles almost all disappeared very abruptly, was akin to a cliff. So they called it the helio cliff. And so we had a new but non-theoretically supported explanation for what had happened. So science is a matter of serendipity often. And I've been lucky in having a number of serendipitous things happen. I won't talk about any of them related to this, although there was certainly a few very serendipitous things happen. But in this particular case, there was a very serendipitous event. So let me just point out briefly. So this is kind of theoretical modeling. This is just a simple picture which shows the density at roughly 1 astronomical unit associated with the solar wind. And you can see, and this is deliberately plotted on a non-log-log scale. So there's log, and this is just sort of distance in astronomical units. And you can see that the density drops significantly. That tiny little bump is the termination shock, the change in density and crossing over the termination shock. This region over there is the inner heliosheath through which the Voyager 1 and Voyager 2 were traveling. And then these are different curves. Don't worry about which is which, but you can see this over there is what the heliopause looks like. So the density jumps very, very significantly when you go from the inner heliosheath to the interstellar medium. There's some complications associated with whether or not there's a bow shock or a bow wave or nothing. But the point being that you get this very large density change. So I was driving to the pool one day. This was shortly after 2012. This was early in 2013. And I got a call from Don Gurnett, who's the principal investigator on the plasma wave instrument on Voyager. And he said, if I said to you that the measured number density is on the order of 0.08 particles per cubic centimeter, where would you say the Voyagers are? And so I immediately said, in the interstellar medium. He said, good, that's all I needed to know, and hung up without telling me anything more about why he had asked this question. So Voyager 1, when it went past Jupiter, its plasma instrument was broken. It was irreparably damaged by the huge radiation and energetic particle fields that are in the vicinity of Jupiter, and so the plasma instrument no longer works. So we can no longer measure what the plasma density or the velocities or the temperature of the plasma is. They're working on Voyager 2, but Voyager 2 is way back. However, the plasma wave instrument is still working. And so what the plasma wave instrument does is to measure small electric fields, and it can measure then various frequencies. And so from those frequencies, you can then infer the electron number density. And so what's plotted on the left side over here is the measured plasma frequency, or the measured plasma frequency that the plasma wave instrument measures. And on the right-hand side is what the number density, the number of particles per cubic centimeter, will be at any given location. Now, the plasma wave instrument was always viewed as something of the poor second cousin of the instrument suite on Voyager 1 and Voyager 2, because once Voyager 1 and Voyager 2 had crossed the termination shock, the instruments didn't see anything. So every time there was an exciting discovery, of which there were many by Voyager, then there would be papers written, and they'd be published in Nature or Science, and there would always be this poor little footnote associated with the plasma wave team that they hadn't actually seen anything. And this was therefore an interesting, if not exciting, result. So nothing had been seen. So shortly after this dispute had begun with whether or not we'd crossed the heliopause, this was the origin of a phone call. At this particular event, the plasma wave instrument suddenly saw something. And what it saw was this rather intense emission in April and through April, May of 2013. Now, they hadn't seen this event over here, which had occurred more or less at the time the crossing of whatever this was had occurred. Remember, that was sort of in late 2012. This was sort of earlier in 2012. The reason they hadn't seen this is they hadn't been back to analyze the data, and part of the reason they hadn't analyzed the data is because the plasma wave instrument gets sort of several months of data that's downloaded at a time, and so it's not downloaded in real time. And so they hadn't been seeing anything, and so I guess they hadn't felt that they needed to go and look at anything urgently. But when this dispute erupted, of course, they started going back and looking carefully at their data, and this was what they saw. So what they saw then was they saw an event that produced radiation, and when you compared what the when you looked at translated what the frequency meant in terms of the density, it was 0.08 or 0.08 particles, or a little bit above particles per cubic centimeter, whereas the number density in the inner heliosheath is on the order of 0.001 particles or 0.002 particles per cubic centimeter, so virtually an order of magnitude lower. And there's no way you can possibly increase that amplitude, not with a large shock, not with anything get it up to this kind of value. So when they saw this, the conclusion was that in fact we had crossed the heliopause at the time we thought we had, and that the magnetic field, and that in fact there was also a well-defined density ramp that was essentially consistent with this very local interstellar medium density. The difficulty of the magnetic field still remained. Why should it be so the change in direction be so small? Well, that kind of gradually worked itself out because a number of us were busy telling Len Belager and Norm Ness and others that in fact you wouldn't expect the magnetic field to change dramatically, because it's a little bit like a magnetic field that's convected onto a blunt obstacle, and it kind of piles up, and as a result this effect of draping leads to a magnetic field that doesn't tip, unless it's very odd, look very different. In any event, so that eventually got worked out, but the exciting thing was this observation that was found by Don Gurnett and the WAVE team, in fact revealed that whatever the origin was, it was essentially something that was related to an interstellar shock wave. And so now we'd also discovered that in fact for the first time we'd seen an in situ interstellar shock. And so Belager and Ness were able to plot out the magnetic field data, and they identified that surprising structure as a shock wave. This was the galactic cosmic ray intensity that I'd mentioned before, where you see the intensity of the cosmic rays is quite high on outside in the interstellar medium, and then drops significantly as you cross the heliopause into the interplanetary or the inner heliosheath, and eventually into the interplanetary medium. So we'd crossed the heliopause, which was about over here. We've got this curious structure that we still don't understand. We've discovered that the interstellar magnetic field is oriented in a direction that's not terribly different. We've also discovered for the first time an interstellar shock. I should add that one of the interesting things about that interstellar shock is that it turns out to be quite different from shock waves in the interplanetary medium, in the sense that it's not a collisionless shock. Shocks in the interplanetary medium tend to be collisionless. This shock actually appears to be a collisional shock. That is, it's mediated by the collisions of particles, which is quite unusual. So there's a blow-up of that. All right, so Voyager 1 in some sense, so I just kind of borrowed this John Gillespie McGee poem that I remember having done as a kid and changed around some of the words, and you can read that if you will. So can you tell me how much time is left?
Still 10 minutes.
Okay. So I thought I'd try to get across some science to some of you, and some of you may find it not that interesting or perhaps less interesting. So I thought I'd try and just pick out two things that I think are of particular interest that to sort of carry away. There's lots and lots of interesting things, but I mentioned that the interstellar media is partially ionized, a mixture of plasma and neutral gas. And it's that interaction that plays, in a sense, a fundamental part in determining how the physics of the interaction between the solar wind and the interstellar medium behaves. The reason for that is that there's a process called charge exchange, and charge exchange is, in essence, is fairly simple. If you have a neutral particle and you have a proton, and if they're moving along together, here, for example, you have a solar wind proton or ion gyrating around the magnetic field wherever it is, and it's missing an electron. And so if I have a neutral hydrogen that comes sufficiently close, the proton over there can snatch the electron from the neutral hydrogen atom. And so what I then do is I suddenly create, instead of a blue proton, I produce a green atom. And so because this thing's gyrating around, as soon as it becomes a neutral atom, it then is no longer confined by the magnetic field, and it'll just bolt off that magnetic field in whatever trajectory that it happened to be neutralized at. And so there, that particle sprayed out at that particular direction. So the charge exchange mean-free path in the interstellar medium is relatively short. It's on the order of about 50 to 60 astronomical units, which on those scales is relatively small. But when you get into the heliosphere part, the inner heliosheath, the supersonic solar wind, the mean free path becomes very, very large. It can become as much as 1,000 astronomical units. So the charge exchange mean free path becomes as large as the problem you're trying to solve. And so there's a question of how do you incorporate neutral hydrogen interactions and plasma. And that led to a very intense debate, of which I was very heavily involved. So the way you would typically, and I apologize, but there are not too many equations, but the way one would typically model the plasma is you would use a sort of continuum description. You would use essentially a description that applies to the gas in the room or the fluid flowing through in a stream or whatever. And you would then add a magnetic field to that. And so you would get essentially the same kind of fluid dynamics equations modified by magnetic fields and electric fields. The complication comes in that when you've got neutrals over these very large scales, they take out energy from the background plasma, and they put it into a new kind of neutral called a pickup ion. And so you end up having source terms that produce energy and momentum, or remove energy and momentum depending on the circumstances in the plasma. And so you have to then calculate how that is all done. And that's where, I mean, this is an exceedingly difficult system of equations to solve at the best of times. When you add then that equation over there, which has to describe the distribution function for the hydrogen atoms, along with these so-called collisional or charge exchange source and loss terms, it's an integral differential equation, and it becomes one of the most challenging problems in sort of space physics or astrophysics. So you can only really solve this numerically, and the way you can kind of solve it, oops, I just left off the kinetic side over there, is essentially you have the two systems of equations. I've left out the magnetic fields, and you essentially couple these two in a complicated way where you solve for the MHD or the gas dynamic equations. That then gives you a distribution for the plasma, which you then use to try to then solve the Boltzmann or the Boltzmann equation for the neutral hydrogen distribution. So you then evolve that. That gives you a new updated distribution, which allows you then to compute the appropriate source terms in your continuum equations, and you then update. So you sort of continually cycle back and forth. And it's a very complicated problem, very challenging computationally. So we've had So computer scientists, it turns out, love this code, these calculations we do, because it's the kind of code that will completely stress any supercomputer in the world. And so we've been fortunate in getting huge amounts of time on some of the fastest supercomputers in the world, because trying to solve this system is perhaps the most stressful thing for a supercomputer to do. But surprisingly enough, you can kind of guess a lot of the answers without doing any calculations except drawing little arrows, and I'll draw a couple of arrows. So the only thing that I want to draw your attention to is that's a picture of the sun and the solar wind. This is the termination shock. In the termination shock, most of the energy is in the kinetic energy of the wind. In this region over here, downstream of the termination shock, you heat up the plasma, so it becomes very hot, typically 10 to the 6 million degrees. Then you've got the interstellar medium, where it's sort of warm, not very exciting, and there's maybe a bow shock which does something. So you can then say to yourself, all right, what happens to the neutral distribution? Well, this is the plasma. The plasma just follows paths. It sees these electromagnetic obstacles, the bow shock, the heliopause, the termination shock, and so that plasma is then deflected in response to that. But neutral hydrogen doesn't care about an electromagnetic obstacle at all. It just plows through magnetic fields without caring what they are. So here I have a neutral hydrogen that's just propagated from the interstellar medium, and I'm going to suppose that I have a charge exchange event happen at that particular point. Well, what happens? The charge exchange event then produces a new proton, but that proton, remember, was deflected by the bow shock. And so the proton is moving off the same kind of trajectory that it started on. And so the new neutral takes on that proton, and so the new neutral is diverted in a slightly different direction as a result of that charge exchange event. The other thing that happened to the protons at that bow shock is they were slowed and they were heated. So that new neutral that I produced is also slowed and heated. So now I've created a slowed, heated, diverted neutral atom. So then let's just suppose I have a charge exchange event that happens inside the supersonic solar wind. So now in the supersonic solar wind, I charge exchange with particles that are, with protons that are moving radially outwards at speeds of 400 to 700 kilometers per second. And so the new neutral is going to take on the characteristics. So it's going to spray out at that same sort of speed in a more or less radial direction and produce a neutral solar wind moving outwards that doesn't care about any of the termination, shock, or electromagnetic arrows. So now I've created from a slow-moving 23 kilometers per second or 26 kilometer per second neutral, I created a hotter diverted neutral, and then I also create a new kind of neutral that's moving outwards back into the interstellar medium possibly, that's moving very fast and is relatively cool. So I can consider okay, let's not worry about any of that. I can consider another neutral and suppose that it, instead of charge exchanging in the supersonic solar wind, charge exchanges in this very hot region. So now what I do is I create a new neutral that has the characteristics of that very hot region. And so now I've suddenly produced a million-degree neutral from 10,000 degrees that I started out with. And I have this million-degree neutral that's moving back out into the interstellar medium. And it can undergo secondary charge exchange. And it can, in fact, then heat the interstellar medium and change the properties of the interstellar medium. And so this very complicated interaction has now produced multiple populations of very different kinds of neutral atoms, all of which have an effect. And I'm going to just scoot through this. All of which can have an effect. So if you take a whole lot of neutral atoms and you slow them, you heat them, and you divert them, what's likely to happen? Well, they're going to pile up. It's going to slow down, and you're going to produce a pileup. So if I go through that huge, complicated code that I described, and ask what happens to the neutral hydrogen, well, that's what I get. I do indeed get a pileup of neutral hydrogen. It's called the hydrogen wall. And it's slightly heated, slightly diverted, and slightly slowed. And so you can predict the existence of that. And moreover, it turned out that in 1996, or 1996, at that same meeting I was talking to was somebody else attending by the name of Jeff Linsky. And Jeff Linsky had heard a talk that I'd given just a few months earlier in Boulder. And he had been sitting at the back of the audience and had been kind of talking to somebody by the name of Priscilla Frisch quite loudly while I was showing these results that we'd computed. And I was getting quite irritated by all of this. Anyway, so Jeff Linsky came down after the talk and said, "Oh, can I take your transparencies?" And for those of you who don't remember, you used to have transparencies that you put on to overhead projectors. They're little plastic things. So I gave him the transparencies, and he said, "Be in the audience at 8. I got something really interesting to tell you." So he came, and so I came to the talk that Jeff Linsky was giving at 8 o'clock, and he and his student Brian Wood had been interested in the deuterium to hydrogen ratio in the interstellar medium for reasons to do with cosmology and not anything to do with this. But what they'd noticed using the Hubble, the Hubble Space Telescope had an instrument, a spectrometer called the Goddard High Resolution Spectrometer. And using that instrument, they were able to look at nearby stars and measure what's called the Lyman alpha absorption associated with the stars. So basically the stars send out Lyman alpha light, and then that light is scattered, absorbed by the intervening neutral material between the Hubble Space Telescope and the star. And so what they noticed was that there was a depletion, there was an absorption of this light, but the absorption amount was more than they expected. They had a very good idea of what, in fact, the absorption should be, but there was a little extra that was unaccounted for. And the only way that Jeff Linsky and Brian Wood could explain this at the time was to postulate that there was a very small cloud that was undetectable, but happened to be slightly hotter, moving at a slightly different velocity and in a slightly different velocity, so slightly different speed and slightly different direction from the rest of the cloud in which it was embedded. And so they said, you know, these are the properties of that weird little cloud that just has to be there. Anyway, so he showed the presentation and he showed the properties that they had derived, and then he had a little yellow sticky note over, and he then lifted up, and they were in fact identical to the properties that we had predicted for the hydrogen wall. So that was the first boundary that was in fact discovered. The hydrogen wall was discovered through this Lyman alpha absorption technique, and that again is an interesting example of serendipity in science. I had no idea what Jeff Linsky was doing, and I certainly wasn't very interested in the D to H ratio, and he at the time was certainly not interested in hydrogen walls, but somehow it came together, and it turned out that it was a very important discovery for both of us. All right, so I think I'm kind of getting tired and getting to the end. So you can do these very exotic models. It turns out that things are not as simple and as stationary as one would like, and so that's what the heliosphere looks like. These are just some examples of the code. This is what those models look like today. They're much, much more sophisticated. They're quite beautiful, in fact, when you put them together. I'm not going to go through that. I thought I'd just sort of finish up very briefly with the IBEX ribbon, since a lot of you have heard about it, and I've pretty much explained all the physics that you need to know to understand the origin of the IBEX ribbon. So IBEX is the Interstellar Boundary Explorer, IBEX. I'm a co-investigator on this, and the very first result, in a sense, that IBEX discovered was quite unexpected, although in retrospect, we should have expected it. So what they saw was this region of enhanced neutral atoms, energetic neutral atoms, sort of painted across the sky when you looked up at it and made these measurements. IBEX is a spacecraft, this one over here, at 1 astronomical unit. And when it's a spinner, and it sort of looks at the sky and it collects all these statistics in these different directions. And rather remarkably, it noticed that there was a region in the sky which was much, much brighter than the surrounding regions. And this then was called the IBEX ribbon. And Priscilla Frisch, an astronomer who actually read some of our modeling papers, realized, in fact, that the orientation of that ribbon was exactly perpendicular to the interstellar magnetic fields that we computed in our models. And so this is the IBEX data, and these solid lines over there are the computed magnetic fields from our models, and you can see that they're orthogonal. In fact, that ribbon correlates perfectly with this little relation, magnetic field in the interstellar medium, B, dotted with the radial direction defined by the sun, is roughly 0. Why is that? Well, you remember I told you about the whole charge exchange process in that little cartoon, and you saw that if you had a charge exchange, when the ion was gyrating around the magnetic field and you suddenly made it neutral, it would then, almost in a flywheel sense, suddenly shoot out in that particular direction once you neutralized it. And so this was, in fact, the idea. You have these supersonic neutral atoms, created for example, in the supersonic solar wind, so that neutral solar wind, or you have neutral atoms propagating out from here. But these neutral atoms propagate from, say, this region over here, propagate out into the interstellar medium as neutrals, and then undergo a charge exchange process and become ions. And so they then start gyrating around the magnetic field. Now, if you can keep them gyrating around the magnetic field for long enough without scattering onto some other form of distribution, so that they stay more or less what's called a ring distribution, what can then happen is then those ions can then undergo a further secondary charge exchange. So now you've got these gyrating ions, and as you charge exchange, they then sort of fill out a space like a, you can imagine just water spraying off the surface of a flywheel. If you happen to be in the right direction and that water sprays, you'll see some of that. And so those particles, in a sense, are almost flung out from the interstellar magnetic field, normal to the interstellar magnetic field, and you can measure them with a spacecraft that measures those things. So you can create then a region that is enhanced in this neutral atom flux. And so you can take a look, and the figures on the left are simulations, and the figures on the right are, in fact, the observations. And you can see that they are remarkably similar. And so the IBEX ribbon can be explained in a very simple way just by that. So that basically brings me to the sort of overarching conclusion. We're beginning to understand the basic physics of the interaction underlying the physics underlying the interaction of the solar wind with the interstellar medium. And I hope I've tried to convey to you the importance of this neutral component in the interstellar medium, which helps shape the large-scale heliosphere. And sort of the work that I haven't really talked about is how the interstellar medium is mediated by the heliosphere itself. So I've kind of mentioned as I went along that there have been controversies throughout this entire process. In fact, in 1996, I was embroiled in a huge controversy with a Russian colleague of mine about how to do some of this work. And I'm not sure that we're still particularly good friends. You heard about the controversy that erupted over whether or not we were in the interstellar medium or whether we were still in the inside the heliosphere. So there have been controversies in this field all along, and some of them have been driven by how do you model this very complicated system. Some of them have been driven by how do you interpret the observations. And of course, you get a bunch of scientists in a room, and they will all have their own opinion and their own view, and they frequently disagree, frequently quite strongly. I got an email, it wasn't directed at me, but I got an email this morning from a very well-known colleague of ours who was railing on about somebody not knowing anything about this and about a particular subject, and why on earth did they think they could even conceive of publishing this paper. So this happens all the time, and so this was something that I felt was probably a salutary lesson to those of you who may not do terribly much science. It's a reminder that science is an extraordinarily social activity, and that views and opinions can depend very much on who you want to listen to.
I figure 75% to you, Mom, and 25% divided between the 5 of us. Either Crowbar, myself, Tom, and the baby. That makes 5% for each one of us.
Billy, you're cheating yourself. If there's 25% divided among the 5 of you, that's 14% apiece.
Oh, no, listen, Mom. I wouldn't cheat you. You know I wouldn't. Now, look here. I'll show you. Look at on this house here. And, 25 divided by 5 is 5. You see, if the 5 won't go into 2, will it? No. But 5 goes into 25 5 times, you see?
Oh, you're wrong, Billy. Now, I'm pretty good mathematician. Now, 5 into 25. 5 won't go into 2.
No.
But 5 goes into 5 once. Now, in the yeah. Now, 5 into 20 goes 4 times. 5 is 25. 14.
No, look, Mom. Now, let me prove it for you. That's education. 5 times 5. 5 times 5 is 25.
Surprised you're learning. I'm surprised that you're learning. Now I'll show you. 14 is 25. 5 times 4 is 20. 5 times 1 is 5. 20 is 5.
You're wrong there because I'll prove it to you. We'll put down 5 14s here. 14, 14, 13. There. Now I'll prove to you by addition that the 5 14s is not 25. 4, 8, 12, 16, 20,
21, 22.
All right, so that's how science really is done. So, okay, thank you.
Thanks a lot for this very nice talk and giving us insight how science really works. Let's see how science here works. Are there any questions? Please.
Could you show once again that slide which you have for the density as a function of time equality?
Oh, okay.
Particle density, I think, the plasma density.
Oh, yes, yes, the spectrogram. Yeah.
It reached an asymptotic level.
Oh. Oh. I hope nobody asked me to go forward. Okay. This one.
Right. I know I think one before, but you had 3 curves in different colors.
Oh. Oh, this one. Mm-hmm. Oh, sorry. Yes.
So let's see the plasma density, isn't it?
Yeah, so that's correct. Yeah.
So, this seemingly asymptotic value, how far would you dare to extrapolate this out?
Well, that asymptotic value is given to me by sort of the boundary condition that I put on. So these simulations are typically in a in the upwind direction. I go to about 1,000 astronomical units. Downwind, I might go to 4, 2, 3, 4, or 5,000 astronomical units. This is a sort of 3D simulation, so they're enormous. We get down to a resolution of about 0.05. But at this point, I think I know what the number density is from various observations that we have at more or less 1,000 astronomical units. So here I've used different number densities. That number density that I chose over there is such that it gives me no bow shock. That plasma density that I use over there gives me a sort of bow wave. It's kind of an interesting solution. And then that plasma density gives me a bow shock, which is mediated by neutrals. So there has been sort of discussion about what plasma density you should use in the interstellar medium, and it's got a lot to do with how the white dwarfs and so forth produce the radiation environment in which the sun resides, and so knowing exactly what the fraction is between charged particles and neutral hydrogen is very complicated. So I get some kind of total density estimate, and then I have to then figure out what the fraction between charged and neutral gas is.
It's that low. I mean, you often take just one CC or the galactic disk when you were.
Yeah, that's right. Yeah. Yeah, that's right. Yeah. Well, well, remember that we're embedded in a warm cloud here. So it's not characteristic of the entire galaxy. Just as the number density in the hot interstellar medium that I showed earlier on, that number density is much, much smaller. It's probably on the order of 0.1 to 1 particles per cubic centimeter. Yeah, that's right. And in that case, it's all ionized. And again, here, we don't know. I mean, there are now fairly good models, but we don't know what the ionization fraction is. So you kind of have to pick and choose. But it appears that if you go and it appears that this is the vicinity of more or less where we might be based on the observations that Gurnett et al. Put out. Yeah.
Are there any further questions? Yeah, please.
I come to you.
Oh, okay.
I have to make sure.
Dankeschön. I would like to ask you, is this correct?
Yes, that's correct. So this is at the JPL.
Is this correct?
Yes, so this is about 13 billion miles, and that's at 100. That's just for Voyager 1 from the Earth, and that's 141 astronomical units. That's correct.
Yes.
And so I had just gone to this website a couple of days ago. This is sort of the.
And this is always is correct.
It's continuously updated. That's correct. Yes.
Okay.
It was the JPL website that you can go to, and you can see how far Voyager 1 and Voyager 2 are. And this is what he was showing.
All the time.
Yeah,
it's
continuously updated every day.
Right.
Yeah, or at least every moment, actually. That's why you see it ticking through.
He goes away from Earth, and then he comes again.
No, it's continuously moving away from the Earth. Well, you've got to be a bit careful. The Earth is rotating. So there are times when it goes a little fast, principle a little.
He comes down, and then he goes.
Yeah, that's right.
Up.
Yeah. So So you got to, they take that whole trajectory into account.
Yes.
It's easiest to look at this number, which is the distance from the sun. At least that's
from the sun.
Yeah, that's second one's from the sun.
This is.
Oh, and then, this is cosmic ray data. So that's just an indication of how many cosmic rays they're measuring on board the spacecraft related to the instrument. Yeah. Okay.
I thank you very much.
You're very welcome.
Yes, Rowan. Any further questions? Please.
It's very heavily shielded, so no, I don't think we're measuring, at least with the cosmic rays. I hope we're not measuring plutonium byproducts or anything. So no, they've sort of tested and checked that all out before they launched, and then of course, they've seen no anomalous behavior, at least no anomalous behavior that can be ascribed to that. They've seen some odd behavior about different things, but that was physically explained in the end.
Okay. Herman?
When do you actually expect to lose the contact to the probes?
They keep playing around with it. They've been switching off instruments as time has gone by in an effort to try to prolong the life. And so currently they're expecting about 2025. I'm not sure, Peter, if you know a better date than I do, but more or less 2025. There was a discussion at the Fall AGU in New Orleans about just what they're doing and when they're anticipating turning it off, and they've done some other tricks that the engineers have figured out to try to prolong the life, but pretty much 2025 is the expected end date, unfortunately.
And is there a special team to receive this signal?
It's all downloaded to the Deep Space Network, and I think they have 8 hours coverage per day. So that was a little unfortunate, because when Voyager 1 crossed the termination shock, of course, it happened during a data gap. And so we didn't actually see the crossing, but once we'd crossed, we knew it was there. Voyager 2 crossed during a time when we were downloading the data, so we were able to see the series of more or less 5 crossings of the termination shock. So the termination shock was kind of sweeping back and forth, and so it crossed the spacecraft 5 times, and so we were able to see in quite some detail, especially with the magnetic field instrument, but also with the plasma instrument, what the structure of the shock looked like. So one of the crossings exhibited a very clear structure that would be associated with a more or less classical quasi-perpendicular shock. But again, we're using 1970s instrumentation, which, is very low cadence, kind of, measures particles slowly, so you don't get, and it wasn't instrumented even to be out there. So much of the interesting physics associated with pickup ions has to be kind of inferred indirectly.
I actually meant the kind of organization. It's probably not a Voyager team creating the signals. It's probably another team who cares also with this data.
Yeah, you know, in the way of most scientists, I don't think they really care too much about the details as long as it gets sent back correctly. But there's a, you know, there is a team associated with the Deep Space Network and the data being processed and sent on to the respective principal investigators. So that gets sent on to Norm Ness gets all the magnetometer data. Actually now Len Balaga, Ed Stone gets all the cosmic ray data. Cremegis gets the low energy charged particle data, and Gurnett his data, and then they process it appropriately. And so the bigger challenge actually, which actually probably a bigger challenge than 2025 with the instrument running out, is that the PIs may run out of time well before then. Unfortunately, Ed Stone is now 82, I think. And, all of the PIs, they started out in their, when Ed Stone was roughly 42 when Voyager was launched. And so all of these people are very senior, and, it's not clear, especially because a lot of the knowledge about some of the instruments, especially the magnetometer, has kind of disappeared. It's never been written down in the way it's documented today. So this is a serious problem about what may happen if Len Balaga or Norm Ness disappear tomorrow, or any of the others.
Okay.
So
I'm sorry. I think there's another question.
Thank you. This last question is an excellent opening to my question, maybe the last one. It seems that you have solved a lot of problems, and you have managed to get the scientists in agreement, more or less, together. So what does remain to be done, and how would you do it?
Well, there's a fairly large effort underway to try to build an interstellar probe. So much of the physics that we've sort of worked through, it's been done on a mixture of sort of very detailed modeling and inferring a great deal from the observations. So if you just think about the plasma alone, for example, everything that we know about pickup ions has not been validated or verified or understood in terms of Voyager. It doesn't measure those energies whatsoever. And so the distributions that we observe are just this small thermal kind of core distribution. So Voyager is very, very poorly instrumented to, in fact, explore the boundaries in the interstellar medium. So we've tried to compensate a little bit by virtue of the IBEX spacecraft. So what IBEX does is measure energetic neutral atoms. It just has two telescopes, IBEX high and IBEX low. And so you can... So to interpret those energetic neutral atom observations requires an exceedingly close interlinking of modeling and the observations. And the modeling itself has, to some extent, driven much of what we understand about the sort of basic plasma physics, perhaps more so than the Voyager spacecraft. So to give you an example, I'd mentioned the heliospheric termination shock. So one of the things that I had done in 1996, it was a very productive year, was to show that pickup ions would be preferentially reflected at a quasi-perpendicular shock, such as the heliospheric termination shock. And so the primary dissipation process was likely to be pickup ions. So then when you ask, and so it transpires that when Voyager 2 crossed the heliospheric termination shock, what it saw was a very cold Maxwellian distribution downstream. It was on the order of 150,000 Kelvin. All of the models had predicted that the downstream temperature, in fact, just the conservation laws tell you that the temperature downstream of this very strong termination shock should be on the order of 1 million degrees. So where's all the other energy gone? when you looked at the Mach number of that shock, it appeared, if you just use the Maxwellian, used the thermal gas distribution, that in fact was a supersonic transition. It didn't look like it slowed down. So we inferred that all of the energy, in fact, went into the pickup ions, which I had predicted in 1996. So that worked out very nicely. But if you look then more closely at what the downstream distribution behind the termination shock should be, it should be comprised of a sort of superposition of a cold thermal Maxwellian distribution, transmitted pickup ions, and reflected and transmitted pickup ions. So I put together a kind of model that describes that distribution downstream. On the basis of that distribution, just about everything that we do now with regard to interpreting the IBEX observations is based on that kind of distribution. And so you then sort of take a sort of long leap forward, and you look at the energetic neutral atom distributions that you're measuring at 1 AU to infer what the plasma proton distribution should have been in order to produce that. So rather remarkably, you end up probing the microphysics of the termination shock, the microphysics of the interstellar medium and of the inner heliosheath here at 1 AU based on that. But that's, there are a lot of huge links that went through, and what one really wants to do is to put together then a spacecraft that can go measure in situ all of these phenomena and establish, in a sense, the ground truth. And that's just one aspect. There's many others, but yeah.
So the many others are probably the right moment to move then to our apéro. So thanks again for this talk to our speaker. And before leaving and going to the apéro, where you are all kindly invited, I would like to briefly make you aware of our next talks. So we have created some posters. All of you that are ProISSI members will receive this as a PDF file. So please feel free to distribute this also to your colleagues and friends if you want to highlight what is happening here. So our next talk will take place on 23rd of May. So it's taking us back on Earth. It's about the Earth's magnetic field by Professor Niels Olsen from the Technical University of Denmark. And I hope to see as many as today here again. So see you soon in May and enjoy the rest of the evening. Thanks a lot for coming.